Hello everyone, I'm Jyoti from BSc Chemistry Honors second year. So this video is specially for visual impaired students and the chapter name is Acids and Bases from Inorganic Chemistry. Let's talk about it. Arrhenius concepts of acid and bases. Arrhenius, a Swedish chemist, was the first to define acids and bases in aqueous solution. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which, when dissolved in water, gives hydrogen's ion H positive. Accordingly, all mineral acids like HCl, HNO3, and H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ions H positive as HCl in water dissociates as H positive and Cl negative, HNO3 dissociates as H positive and NO3 negative, and H2SO4 as 2H positive, SO2 SO4 to negative. Arrhenius named these acids which dissociate completely in water as strong acids. Um, there are other acids like acetic acid, carbonic acid, and phosphoric acid, which, when dissolved in water, do not dissociate it completely into ions. As a result, an equilibrium set up between the ions and undissociated acid molecule, as shown below. Arrhenius named these acids as weak acids. According to Arrhenius, base is a substance which contain hydroxyl group and which, when dissolved in water, give hydroxyl ions. Thus substances like NaOH and KOH, which when dissolved in water dissociate completely to give hydroxyl ions. Arrhenius named these bases which dissociate completely in water as strong bases. There are substances which do not completely dissociate into hydroxide ions. Arrhenius named these substances as weak bases. For example, substances like NH4OH, MgOS2, ALOS3 do not dissociate completely, give OH negative ions, and can be written as given hydrogen ions obtained from the acid and hydroxyl ions obtained from the bases combined together to form unionized water. Arrhenius described this combination of H positive and OH negative ions are neutralization reaction. Arrhenius concept is very simple to apply and explains a number of phenomena like neutralization, hydrolysis of salts, strength of acids and bases. However, there are certain limitations which are described below. Arrhenius concept of acids and bases applicable only in aqueous solution. This concept fails to explain the acid or base behavior of substances in non-aqueous medium such as liquid ammonia, liquid sulfur dioxide, alcohol, etc. Arrhenius concept fails to explain the acidic character of substances like CO2, SO2, and SO3, etc., and basic character of substances like NH3, Na2, CO3, and CaO, etc. Arrhenius concept also fails to explain the reaction between an acid and a base in the absence of water. Although Arrhenius' concept of a certain base suffers from a number of limitations, yet the concept is very useful and informative for elementary approach. Bronsted-Lowry concept. Arrhenius' concept of acid and bases was further improved by Bronsted-Lowry. Both Bronsted, Danish chemist, and Lowry, an English chemist, in 1923 incidentally introduced the same definition for acids and bases. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton H positive, whereas a base is a substance which can accept a proton H positive. In other words, an acid is proton donor, whereas a base is proton acceptor. As a result, Lowry-Bronsted concept is sometimes called the proton donor acceptor concept. It can be represented as given below. According to Bronsted-Lowry, a neutralization reaction involves the release of the proton by an acid and the acceptance of that proton by a base. For example, the reaction between HCl and NH3 to form the salt ammonium chloride can be represented as the curved arrows show how electrons must rearrange to result in the transfer of hydrogen atom from the acid to base. The unshared pair of electrons on the nitrogen of ammonia is attracted by the partial positive charge on the hydrogen in the polar hydrogen chloride molecule. A comparison of the structures of the reactants and products shows that the hydrogen atom which was bonded to chlorine in the reactant is bonded to nitrogen in the product. Thus, the proton has been transferred from chlorine to nitrogen to act as a Bronsted-Lowry base. Its species must have at least one unshared pair of valence electrons so that it can form a covalent bond to the proton. To act as a Bronsted-Lowry acid, a species must contain at least a one hydrogen atom that is attached to an atom that is more electronegative than hydrogen. It is important to note that the above examples that water acts as base with respect to hydrochloric acid and sulfuric acid. Interestingly, water acts as acid with respect to the ammonia, such as substance which acts as both as an acid proton donor as well as proton acceptor is called amphoteric or amphoprotic substances. Conjugate acid base pairs. Let us reinvestigate a reaction between an acid and base. HCl being acid donates as a proton and from Cl negative ion and form Cl negative ion, whereas ammonia being a base accepts as proton and form ammonium ion. Now the chloride has a tendency to accept the proton, whereas ammonium has a tendency to donate proton. In other words, an acid donates a proton and becomes the base. A base accepts a proton and becomes an acid. Thus, a base formed from an acid is regarded as the conjugate base of the acid. Similarly, the acid formed from a base is called conjugate acid of the base. In the example above, the between HCl and H3, Cl negative is the conjugate base of HCl, and the NH4 positive is the conjugate acid of the base NH3. Acids are bases that are related by the loss or gain that acids and bases that are related by the loss or gain of H positive ion are called conjugate acid base pairs. The Cl negative and HCl negative and H4 positive and S3 are conjugate acid base pairs. We can represent acid base pairs as given below. A substance is capable of showing acidic character only if other substance is capable of accepting the proton, that is a base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not an acid in benzene because benzene does not accept H positive from HCl. Not only neutral molecules but cations and anions may act as acids or bases. Both Arrhenius and Bronsted-Lowry concept require an acid to be a source of proton. Thus, all the Arrhenius acids are Bronsted-Lowry acids. According to Arrhenius, a base is a substance which gives OH negative in solution, whereas according to Bronsted-Lowry, a base is a substance which can accept a proton. For example, carbonate ion cannot give OH negative ions in aqueous solution. It therefore cannot be an Arrhenius base. Thus, all Bronsted-Lowry bases are not Arrhenius bases. Limitation of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcomings of Arrhenius concept, yet it could we are not answer some of the well-established reactions. For example, it cannot explain the reaction between acidic oxides like CO2, SO2, and SO3 with the basic oxides like CaO, BaO, and MgO, etc. that takes place even in the absence of water. Clearly, in the reaction between CO and SO3, there is no proton transfer involved in the reaction. The acidic nature of compounds like BF3, FeCl3, and AlCl3. Lewis' concept of acids and bases. Jean Lewis in 1923 proposed a more general definition of acids and bases, which is based upon the uh, def- donation and acceptance of electron pair. According to Lewis concept, an acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbitals to accommodate one or more pair of electrons can act as a Lewis acid. On the other hand, a base is an electron pair donor. It means that any substance with unshared pair of electrons can behave as Lewis bases. Thus, the acid-base or neutralization reaction involves the formation of a coordinate bond between the electron pair donor and the electron pair acceptor. For example, the reaction between boron trifluoride and ammonium is typically Lewis acid-base reaction. Lewis acids. According to this concept, Lewis acids are classified as as molecules having central atom with incomplete octet of electrons. Boron trichloride, boron trifluoride, aluminum trifluoride, or etc. are acids of this type. It is clear that the central boron and aluminum atom have only 6 electrons. Simple cations. All the cations are short of electrons and can behave as Lewis acids. Large sized cations like Na positive, K positive, C2 positive, and Be2 positive, etc., behave as weak Lewis acids. This is because these have little tendency to accept electrons. On the other hand, small sized cations such as H positive, Az positive, Li positive ions have a strong tendency to accept the pair of electrons. Uh, It was H negative, Ag negative, and Li negative. Ions have a strong tendency to accept the pair of electrons and are strong Lewis acids in no, it was Ag positive. In addition, higher charged cations have a higher tendency to accept electron pairs relatively to lower charged cations of the given metal. These all were cations that it was H positive and Az positive and Li positive. For example, SN4 positive is stronger Lewis acid than SN2 positive. Then some of the typical examples of Lewis acid base reactions are as given below. Molecules in which the central atom has available d orbitals and may acquire more than 8 electrons. Compounds such as AlCl3, SiF4, SnCl4, SPF5, SO3 are Lewis acids, whereas the central metal atom can explain its valence shell. Molecules with a multiple bond between atoms of dissimilar electronegativities. Carbon dioxide represents an interesting example of double bond between carbon and the more electronegative oxygen atom. Oxygen, being more electronegative, has a tendency to attract the shared pair of electron more towards it in CO2. As a result, it acquires positive charge on the carbon atom and becomes electron deficient and attached with the oxygen of the hydroxide. Lewis bases. According to the concept, Lewis bases may be classified as one of the following types. Negatively charged anion species. All the negatively charged species are Lewis bases because they are rich of electrons and have a strong tendency to donate electron pairs. Cl negative. These are some common examples such as Cl negative, O2 negative, OH negative, Ns2 negative. The greater the charge density on the anion, the stronger is the base. Neutral molecules with one or more than the unshared pair of electrons. Molecules with unshared pair of electrons act as Lewis bases. For example, Ns2H2O, R2O, R2C double bond acts as electron donors. Alkenes and alkynes with multiple bonds also form coordinate bonds with metal ions in organometallic compounds. Acid base reactions. According to Lewis concept, some of the typical acid base reactions involving the formation of a coordinate bond between a Lewis acid and Lewis base are summarized below. It is important to note that an empty orbital is being created on the sulfur atom by moving a pair of electrons from the double bond on the oxygen atom. Combination of cupric ion with ammonia is given below. Some examples are also given, that is combination of sternic chloride with ethers to give an adduct. Lewis acid base concept discussed above is widely used because of its simplicity in many acid base reactions. In spite of its wider applications than Arrhenius and Bronsted-Lowry concept has several disadvantages which are discussed below. Lewis concept is too general and consider all reactions forming a coordinate bond way, that is acid base reaction. This is however not true always. According to Lewis concept, transition metals that form compounds with carbon monoxide such as NiCO4 etc. are acid-base reactions, which is not performs acid-base reactions, which is not correct. Formation of a coordinate bond between an acid and base is the basis of Lewis concept. The well-known acids like HCl, HNO3, and H2SO4 do not form any coordinate bond bases such as NaOH or QH. Accordingly, HCl, HNO3, and H2SO4 should not be acids according to Lewis concept. Lux flood concept of acid and base. A new concept of acid and base was proposed by Lux in 1939. This concept was further proposed by Flood. According to Lux flood concept, an acid is any substance which accepts an electron, whereas a base is any substance which gives up oxide ion. According to Lux flood concept, substances that show a tendency to lose as well as gain an oxide ion are termed as amphoteric. Zinc oxide represents an interesting example of amphoteric character. Thus, This concept of flux flood is very useful at high temperatures, especially in glass ceramic industry and metallurgical operation. The concept of flux flood can also be extended to halides and sulfides. Unsavage concept of acid and base. Unsavage concept of acids and base is very general and takes into consideration all the concepts of acid and bases proposed by Arrhenius, Lowry, Bronsted, and Lewis acids. In addition, which concept includes all oxidizing agents as acids and all reducing agents as bases. Thus, according assign a which concept. An acid is a substance that reacts with the base, gives up cations, accepts anions for electrons. Similarly, in Azanovich concept defines a base as a substance that reacts with an acid, gives up anions, or combines with the cations. Right now, which concept is very useful as it classifies all examples of acids and bases to its two general solvent system concept. The solvent system concept of acids and bases was postulated by Caddy in 1928 to the Lowry-Bronsted concept, and it is applicable to both protonic as well as non-protonic solvents. An acid is a substance which either by direct dissociation or by the interaction with cationic character of solvent. A base is a substance which either by direct dissociation or by the interaction with the solvent gives the any characteristic to the solvent. Here are some examples given below, like NS3 and of CSCCOH, etc. Similar to Arrhenius concept, neutralization reaction may be represented as the combination of cationic characteristic of the solvent with the anionic characteristic of the solvent to form the solvent molecule in an non-aqueous medium. Some of the neutralization reaction in various solvents are given below. Types of solvent such as protic and anaprotic solvent. Solvent which contain a hydrogen and can lose hydrogen in the form of proton are called protonic. And common example of protonic solvents are H2O and H2S. And the solvents from which hydrogen cannot be obtained in the form of proton are called aprotic solvents such as CS3, and C6H6, etc. Acidic, basic, and amphiprotic solvents which have a strong tendency to give protons are called acidic, while which strong affinity for have a strong affinity for protons are called basic. And the which shows both type of characterism for direct type solvents which display both acidic and basic properties. And ionizing and non-ionizing solvents which undergo self-ionization are called ionizing solvents which do not ionize are called non-ionizing solvents. Relative strength of acids. It is the extent of ionization of an acid which measures the strength of the acid, where K equals to H positive into A negative upon HA. Pk equals 2 minus log of Ka equals to 1 upon log of Ka. A larger value of Pk means that the acid is little dissociated, implies that acid is weak. Larger the value of Pk, the weaker is the acid. Friends, and acidic strength. We have learned that the relative strength of acids in aqueous solution can be easily expressed in terms of pKa value. The higher the value of pKa, the weaker is the acid, and vice versa. The pKa values of the hydrides are given as below. Let us evaluate how the acidity of binary hydrides depend upon the nature of compounds, its molecular structure of position in the periodic table. A comparison of pKa values of binary hydrides reveals that on moving from left to right across a period, the strength of the binary acid increases. For example, the acidic strength of binary acids along the second period decreases as HFH2 and S3CH4. The observed trend can be easily explained on the basis of electronegativity of the element as one moves left to right along a period. It is very important to note that size does not change greatly across a period. It is very important to note that with the increase in electronegativity of the central atom, the tendency to pull the electron pair from the hydrogen increases. This facilitates the release of hydrogen in the form of proton and makes the hydride ion more acidic in character. On similar considerations, we can explain how the acidic strength of binary hydrides of third period decreases as HClH2sps3. A comparison of pKa values of binary hydrides reveal that the relative strength of acid increases as one moves down the group, as inspection of the pKa reveals that hydrogen fluoride is weaker acid than hydrogen iodide. The actual order of acidic strength down the group in periodic table cannot be explained solely on the basis of electronegativity constituents. For example, in group 7, chlorine being the most highly electronegative element should pull the electron pair towards itself in HF. As a result, the release of hydrogen in the form of proton should be highly facilitated, making HF the strongest acid. In fact, HF is the weakest acid. The anomaly can be explained if we take into consideration the size of the central atom. As we move down the group, the electronegativity decreases but the size of the atom increases. The effect of increase in size of the atom is more than the decrease in the electronegativity value of the central atom. A proton can be more easily removed from a hydride in which the central atom is bigger in size as compared to the an atom which has smaller size. The overall reaction can be done in following steps which are given below. Strength of organic acids. Organic acids possess either a carboxylic acid or a phenol group in their formulae. These acids are capable of ionizing and hence releasing hydrogen ion H positive in solution. The acidic strength of these compounds is influenced by two factors, namely inductive effect and resonance. Let us discuss how these two factors influence the strength of the carboxylic acid. Inductive effect. The acidic character of the carboxylic acid is due to the cleavage of the OH bond in the COOH group. As a result of cleavage, the hydrogen ion is released as substitution of electron withdrawing groups, increases the acidic strength of the aliphatic acids. This can be easily explained in case of CH2COH, where X is an electron withdrawing group. The introduction of an electron withdrawing group X gives a positive charge to the carbon atom to which it is attached. This positive carbon in turn influences the electron distribution in the adjoining bonds by withdrawing electrons due to the positive charge. As a result of the OH bonds become weak and the ionization of the proton becomes easier than in absence of this effect. Thus, the presence of chloride in chloroacetic acid makes it as far stronger acid than acetic acid as shown below. Groups that increase the positive charge on the adjacent carbon atoms are called electron withdrawing and have I plus positive effect, while those increasing the negative charge density have negative effect. Since the inductive effect increases with the increase in the number of substituents, it means that the strength of the acid should increase with the number of electron withdrawing substituents. Thus, trifluoroacetic acid is more stronger than the difluoroacetic which is turned in more stronger than fluoroacetic acid. Electron reducing groups like CS3 with the plus I effect increases the electron density on the adjacent carbon atom as well as on the carbon hydrogen group. This discourages the cleavage OH bond and lowers the strength of the carboxylic acid. We have already learned that smaller the pK value, stronger is the acid. Resonance trichloroacetic acid with pK value 0.65 is strongest all of the listed values acids in table. Resonance effect plays an important role in determining in the quality of which bond and hence influences the acid strength of carboxylic acids. The resonance effects differentiates clearly between the aliphatic and aromatic carboxylic acid. For example, benzoic acid is stronger acid than the saturated and like cyclohexane carboxylic acid. It is because the phenyl group is exerting an electron withdrawing effect, whereas the alkyl group is exerting electron donating effect, as evident from the experimentally determined pKa values. However, substitution of electron withdrawing groups in the benzene ring increases the acidity of benzoic acid by resonance effect. The resonance effect of nitro group is more dominant in the ortho-para position but not in meta position. Effect of solvents on the acid strength. Leveling effect. The strength of an acid or a base depends largely on the nature of solvent used for the dissolution. Let us consider the dissolution of hydrogen chloride in three different solvents with ammonia, water, and sulfuric acid. One can clearly see that HOClO is a strong constant acid in NH3, a weak base in water, and strong base in H2SO4. The acid acidity and basicity of a protonic solvent plays an important role in choosing a solvent for a chemical reaction. The strongest acid which is available in a protonic solvent is that which results from the self-ionization of the solvent. Likewise, the strongest base available is the which results from the self-ionization of the solvent. Let us consider examples. In aqueous solution, the strongest acid which can exist and which can be available for the reaction is hydronium or the hydronium ion. It means all the strong acids known as to the chemist appear to have exactly equal throw in chemical strength in aqueous solution. This results from the fact that acids such as perchloric, hydrobromic, nitric, and hydrochloric acids are all stronger proton donors than the hydronium ion. Thus, all these acids react completely with water to give hydronium ion. It means that acids stronger than H3O positive are level to the strength of H3O positive when placed in aqueous solution. In other words, water levels all strong acids, namely HCl4, HHB or HNO3HCl to the strength of H3O positive as shown below. Similarly, the very strong base such as hydride, amide ion, and the ethoxide ion all react completely into aqueous solution to yield hydroxide. It means all these strong bases are leveled to the strength of H negative ion on reaction with water. In other words, solvent water levels all these strong bases to the strength of the acid of water. A vigorous reaction occurs with the brisk evolution of hydrogen gas, and the resulting solution is found to be solution of sodium hydroxide. Similarly, reaction occurs when the base like NaNH2 and sodium ethoxide are added to water. In order to compare the relative strengths of strong acids and bases, the selection of the solvent is very important. The solvent selected should be such that it ionizes the strong acids and bases to different extents. Acetic acid can be used as differentiating solvent because strong acids like HCl4, HHBr, HNO3, and HCl will ionize to different extent in acetic acid. Acetic acid is poor proton acceptor. Perchloric acid reacts completely, that is protonates completely acetic acid, whereas other acids do not react completely because of incomplete protonation of acetic acid by the other acids. On the basis of relative strength of the different ionization of these acids, acetic acids can be arranged order HCl4, HHB or HCl2SO4, HNO3. Acetic acid is leveling solvent towards B bases such as Cn negative, H negative, OC2H5 negative, and H2 negative. This is because acetic acid reacts with the bases and level them to the strength of the citrate ion. CS3CO negative, however, strongly basic solvents such as liquid ammonia acts as differentiating solvent towards bases. Thus, it may be concluded that acidic solvents tend to differentiate between acids and level of bases, whereas basic solvents tend to differentiate between bases and level of acids. To summarize, all acids and bases stronger than the characteristic autoionized ions of the solvent will be leveled off by the solvent, whereas acids or bases weaker than the autoionized ions of the solvent will remain in equilibrium. Strength of oxoacids. The hydroxides of reactive metals are ionic compounds and are strong bases. However, hydroxides of non-metals are molecular compounds and are acidic. The oxoacids can also be considered as derivatives of water and can be represented by the formula EOH, where E is the non-metal which determines the acidity of compounds. The strength of oxoacid depends upon the combined effect resulting from size of the atom E, electronegativity of the atom E, and inductive effect of the solvents substituents present on E. A small, highly electronegative atom E will pull the shared pair of electrons between EU bond mod more towards itself. In turn, the oxygen will pull electrons from hydrogen atom in the OH bond and makes the proton to dissociate easily. This makes the compound EOS to behave as an acid. Thus, the higher the electronegativity of E, the more easily the proton is lost, and consequently stronger is the oxo acid. The acidities of the oxo acids are also related to number of additional oxygen atoms attached to the atom E. In these compounds, the acidity increases with increasing oxidation number of the atom E. In the series of oxo acids, fluorine, the acidic strength increases in the following order: All these acids have only one protonated oxygen. Periodic perchloric acid has two, chloric acid has two, and chlorous acid has one. Perchloric acid has three, chloric acid has two, and chlorous acid has one atom additional oxygen atom. These additional oxygen atoms tend to withdraw more electron density from the hydrogen through the intervening chlorine atom. As a result, polarity of OH bond increases more in case of acids containing larger number of oxygen atoms. In general, oxides without extra oxygen are weak. Oxides with extra oxygen atom are moderately strong. This can be explained in terms of stability of conjugate base formed by the loss of H positive ion from the corresponding acid. Let us consider all the non-hydroxylic oxygen atoms attached to chlorine atom by a double bond. Ionization of proton from the OH bond forms an ion that is stabilized by the charge distribution in an ion. The greater the number of pi or double bonded atoms, the greater is the delocalization of the charge. Consequently, stronger is the acid. We have already learned that with the increase in the oxidation state of the central metal atom, the acidity of the acid increases, as given below. We know that the association of a proton in an acid is possible only by the hydrogen atom attached to the oxygen rather than hydrogen directly connected to the central metal ion. The structure of hypophosphorus acid has only one OH bond. The second oxygen atom is unprotonated. As a result, S3PO2 is monobasic acid, gives only one hydrogen as positive. On the other hand, S3PO3 and S3PO4 has two and three protonated oxygen atoms respectively. We have already shown in case of oxochlorine compounds that the acidic strength increases as the number of non-protonated oxygen atom increases. However, there is only one non-protonated oxygen atom in all three phosphorus compounds. In this case, it means that the effect of non-protonated oxygen atom is the more for one OH group in S3PO2, less for two OH group, and less for three OH groups. Empirical relationship for calculating pKa of an acid. Linus Pauling formulated an empirical relationship to determine the strength of various oxo acids that can be represented as OEOH. The successive pK values of oxo acids usually divided by pKa unit. It is interesting to note that the number of OH groups appear to have little no effect on the strength of the acid resist formulation. Another empirical relationship for the calculation of pK on acid has been developed by resist formulation. Uh, pK equals to 8.0 minus m into 9.0 plus n into 4.0. Um, Acid strength of hydrated cations. Hydroxides of reactive metals are strong bases, whereas hydroxides of non-metal of elements near the border line between metals and non-metals. The periodic table means that they can react either as acids or bases. With the acids, they react as aluminium hydroxide offer a beautiful example. When um, when to a solution of Al2O63 positive, a strong base such as potassium hydroxide is added, protons are transferred from the hydrol- hydra- hydrated hydrated ion to the base. The following reactions that takes place are addition of H negative ion shifts all the four equilibria shown above the right. As hydroxide ions are added to a solution containing Al263 positive ions insoluble, which written frequently as LOS3 is precipitated out, which results in the presence of excess of H negative ions. If a solution of strong acid is added to a solution containing yellow H4 negative ions, H positive reacts with OH negative ions to form water. As OH negative ions removed, all four equilibria shift to the left insoluble precipitates and then re-dissolve. Since the reacts with either acid or base, it is amphoteric in nature. It is important to note that when protons are transferred from hydrated cations, an OH bond breaks just as it does when protons are transferred from oxoacid. Equilibrium constant for hydrolysis of hydrated cations can be measured. A close inspection of table that if charge and electronegativity are similar, then the smaller the radius of the ion, the more acidic ion it is. Thus, the order of acidity among alkali is K positive to Na positive, then Li positive. It is obvious that the acidity of hydrated cations of alkali and alkaline earth metals decreases down the group. If radii and electronegativity are similar, as it is case of Na positive and Ca2 positive, then the higher is the charge on the cation, the more acidic the hydrated ion. If one moves across a row of the periodic table from left to right, ionic radii decreases and charge increases. If charge and radii are similar, the greater the electronegativity of metal, the more acidic the hydrated ion. Let us compare the case of Mg2 positive and Zn2 positive. In case of zinc, the electronegativity is more, hence the cationic zinc more acidic than magnesium. The hydrated L3 positive and with the high charge, small radius and relatively high electronegativity for a metal is by far the most acidic cation listed below. Role of solvent on the strength of Lewis acids and bases. A solvent plays an important role on the strength of Lewis acid and base. A Lewis acid on hydrolysis may produce an acid stronger than Lewis acid itself. For example, boron trichloride, which is Lewis acid, undergoes hydrolysis with the evolution of hydrogen chloride. The sequence of steps involved in the hydrolysis are outlined below. First one is the first step involves the attack of water molecule with the lone pairs of electron on the vacant 2p orbital of boron. A lone pair of electron from water is donated to empty orbital of boron with the formation of coordinate bond. Second step involves the loss of HCl molecule. The donating the it's doing so one of the chloride BCl3 is replaced by one OH group. Third step involves the repetition of the both steps till all the chlorides uh, chlorines are replaced by hydroxyl groups and one gets boric acid S3PO3. Another interesting example where the role of solvent is greatly appreciated is the hydrolysis of silicon tetrachloride to afford silicic acid. The distinguishing feature in the hydrolysis of boron trichloride and silicon tetrachloride is the presence of vacant 3d orbital. In case of silicon, the mechanism of hydrolysis is the same, accepting that the water molecule attacks on the vacant 3 orbital of silicon, forming an adduct involving coordinate bond between silicon and oxygen. The adduct formed losses HCl molecules in step till all the chlorine atoms are replaced by OH group, yielding finally silicic acid SiUH4 as shown below. Thanks for watching.